So mathematics for machine learning practice final exam part 2, picking up with number 5. Find the extrema of f of x, y, z equals x squared plus 2y squared plus 3z squared plus xy plus yz, subject to the constraint x squared plus y squared plus z squared equals 4. Part A, construct the Lagrangian. Part B, derive the stationary equations. Part C, find all critical points. Part D, determine the global maxima and minima. And Part E, interpret the problem geometrically. So let's see here. Um, Constrained optimization and Lagrange multiplier. So f equals x squared plus 2y squared plus 3z squared plus xy plus yz. And f equals the following, that row x, y, z, m, and then column x, y, z. So with m, first row 1, 1 half 0, second row 1 half 2, 1 half, third row 0, 1 half 3. So our constraint is x squared plus y squared plus z squared equals 4. And here we have the extrema of x transpose mx on the sphere occur along the eigenvector of m. So our eigenvalues are going to be lambda equals 2, 2 minus square root of 6 over 2, and 2 plus square root of 6 over 2 for the respective lambdas. Okay, and here for the norm of x squared, that equals 4. So f min equals 4 times 2 quantity, 4 times the quantity 2 minus square root of 6 over 2. That's going to equal 8 minus 2 square root of 6. F max equals 4 times quantity 2 plus square root of 6 over 2. That equals 8 plus 2 to the square root of 6. And geometrically, this is a Rayleigh quotient problem on a sphere. Okay, so moving along now to number 6. So number 6, we want to consider this objective here that we have f of x equals 1 half x transpose qx minus b transpose x. So here, let's see what we have. Derive the gradient, where q is symmetric, positive, definite. Okay, so here, part A, derive gradient descent iteration. Part B, show convergence occurs if and only if learning rate satisfies 0 is less than alpha is less than 2 over lambda sub max. Part C, derive convergence rate in terms of condition number, kappa of q. Part D, explain why L conditioning slows learning. And part E, for q equals this first row 8, 2, second row 2, 4. Find the largest allowable learning rate. Okay, so this is a gradient descent convergence theory problem. We'll go over this quick overview. So the gradient del f, that's qx minus b. So gradient descent is going to be x sub k plus 1 equals x sub k minus alpha times the quantity qx sub k minus b. We're going to let x star equals this q inverse b. Then x to the x sub k plus 1 minus x star equals that quantity I minus lambda q. I minus alpha q. My apologies. That's why I need caffeine. Times x sub kappa minus, or x sub k minus x star. So our convergence requires rho I minus alpha q being less than 1. And since q is symmetric, positive, definite, this means this absolute value of 1 minus alpha lambda sub I is less than 1 for every eigenvalue lambda sub I. So therefore, 0 is less than alpha is less than 2 over lambda sub max. So the optimal fixed learning rate is alpha star equals 2 divided by lambda sub min plus lambda sub max, with convergence factor kappa minus 1 over kappa plus 1. So for q, first row 8, 2, second row 2, 4, the eigenvalues are 6 minus 2 square root of 2 and 6 plus 2 the square root of 2. So building on that, lambda sub max is 6 plus 2 the square root of 2. And the largest allowable learning rate is going to be this 0 less than alpha less than 2 over 6 plus 2 root 2, which is equal to 1 over 3 plus square root of 2. So alpha is less than 1 over 3 plus square root of 2. Okay, so that's number 6. Moving along now to number 7. Sorry about the delay. So we have the distributions there. P equals 0.4, 0.35, 0.25. And Q is 0.5, 0.2, 0.3. So we'll let the distributions be these two respectively. Part A, compute the entropy H of P. Part B, compute the cross entropy HPQ. Part C, compute KL divergence. Part D, we want to prove the following here for D sub KL. And part for Kullback-Leibler. And part E, explain why minimizing cross entropy is equivalent to maximum likelihood learning. So this is information theory and Kullback-Leibler divergence, KL divergence. So entropy here, entropy of P equals this negative sum, the sigma I, p sub I log p sub I. So this entropy here of P, that equals negative this quantity 0.4 log 0.4 plus 0.35 log 0.35 plus 0.25 log 0.25. Now from here we get the cross entropy, and that's going to equal negative this sum I, a p sub I log q sub I. So this cross entropy equals negative quantity 0.4 log 0.5 plus 0.35 log 0.2 plus 0.25 log 0.3. So our KL divergence here, that's going to equal this sigma, this I. So for this whole sum, p sub I log p sub I over q sub I. So we're going to get for the KL divergence of P relative to Q, that's going to equal 0.4 log 0.4 over 0.5 plus 0.35 log 0.35 over 0.2 plus 0.25 log 0.25 over 0.3. So numerically, using natural logs, for this entropy we get 1.0805, and for the cross entropy 1.14121, and then for the Kullback-Leibler we're going to wind up with about 0.0616. It could come out to 0.061 depending on how you round earlier. So the non-negativity follows from Gibbs inequality. So for this Kullback-Leibler, greater than or equal to 0 with equality if and only if P equals Q. Cross entropy satisfies the following. So the cross entropy equals the entropy plus the Kullback-Leibler. So that KL divergence of P relative to Q here. And since our entropy is fixed with respect to the model, minimizing cross entropy is equivalent to minimizing KL divergence, which is equivalent to maximum likelihood estimation. Okay, so that is number 7, and moving along now to number 8. See, okay, that looks like it's set there. So suppose prior distribution, we have theta that is distributed as n 0, 1, and observations satisfy this x of 1. We have the following with this theta distributed as n theta comma sigma squared, where sigma squared is known. Part A, write the likelihood. Part B, compute the posterior distribution. Part C, derive the posterior mean. Part D, show that the posterior variance decreases and then approaches infinity. And Part E, explain the relation to Bayesian linear regression. So this is a Bayesian inference problem. This is an overview of it. So prior for this theta here distributed as n 0, 1, we have the following likelihood, which was given up here. So the likelihood for this, this is going to be proportional to this exponential of -1 over 2 sigma squared, And then we have this sum I equals 1 to n, x sub I minus theta, that quantity squared. So the posterior is Gaussian. We're given the following, where conditions here, where our tau sub n squared equals 1 plus n over sigma squared raised to the negative 1 equals sigma squared over sigma squared plus n. And our mu sub n equals tau sub n squared equals this n over sigma squared x bar, and that equals n x bar over sigma squared plus n. And as n approaches infinity, this tau sub n squared equals sigma squared over sigma squared plus n approaches 0. So we could say the posterior concentrates around the true parameter, and this is the scalar version of Bayesian linear regression, sorry, with design matrix equals A, column of ones. Okay, thank you very much, and that was part 2. Have a great day.